Hi everyone, we're going to be talking about antiderivatives today, which is basically given a derivative, we want to work backwards to figure out what the original function was. So just a couple of things about notation that we'll be using for antiderivatives. Generally, we write an antiderivative using different notation than we would write a regular function or derivative, and the way that we denote that is by using a capital letter. So we denote antiderivatives with capital letters. And I want to talk a little bit about the definition, but then we'll kind of look at an example to see what this means because it's a little bit wordy. But a function capital F is called an antiderivative if the derivative of big F is equal to the original function for all x in the domain of F. So what that looks like, and we'll get this quick example, if I were to tell you that this is the function that I want to take the antiderivative of, this is really saying that this is a derivative of something already. And I want to know what function big f of x has a derivative that's equal to 3x squared. So if I think about what that would be, or if I'm kind of almost reversing derivative rules here, think about popping that 3 back up as the exponent. That would tell me that the original function that I started with would have had to be x to the third power. And that's because if I were to take the derivative of this big f of x function, using the power rule, dropping that 3 down and decreasing the exponent by 1 would give me the 3x squared. So that's saying that the derivative of this big F function, or the antiderivative, is equal to the original function f. So that's what this notation is talking about up here. So that's basically the idea of what we're doing today. So we're going to look at an equation or a given expression, and we want to figure out what was the original function that we started with, if this was kind of like almost our derivative function. So we'll kind of go through a couple of quick examples here. So if I were to say this is the function that I'm looking at, so f of x equals 2x, I want to know what is big f of x, or what function would have had to start with in order to get a derivative that was 2x. That would have to be x squared. And that's because if I were to take the derivative of this big f of x, that would be 2x. So for trig derivatives, it might help to write out your original, or trig antiderivatives, it might help to write out your actual trig derivatives. So we know that if f is sine, its derivative is cosine. So if I know that this function that I'm working with is cosine, and I want to work backwards to figure out what the original function is, that would tell me that my big f of x would have had to have been sine. Because if I take the derivative of sine of x, derivative of sine of x is cosine of x. This f of x equals 3. So if we think about what we would have had to start with to get a constant as a derivative, our big f of x would have had to have been some sort of linear function. Because if we were to take the derivative of 3x, the derivative of 3x would just be 3. And then this last one's a little bit tricky, and we're going to be talking about a power rule that will help us with something like this if it's not as obvious as maybe like 2x or 3 would have been. If I want to figure out what I would have had to start with in order to get a derivative that's x to the third, a lot of the times I like to think about the exponent first. So if we think about to get a derivative, we would have had to decrease the exponent by 1. So I must have had to have started with an exponent of 4 here, because if I drop that down and decrease the exponent by 1, that's what would give me the exponent of 3. But then I would have had to have some kind of number here that would have canceled out in order to just get a 1 in front of the x to the third. And that number here would have had to have been 1/4. Because if I drop down the 4 and multiply by 1/4, that's what would have given me that 1 in front of the x to the third. And again, this is because if I were to take the derivative of this, dropping down the power 4 would cancel out the 1/4, and then decreasing the exponent by 1 would give me a power of 3. But there's a slight problem with these big f of x functions here. We know that if I were to call big f of x maybe like x squared plus 3 here, and I were to take the derivative of this, the derivative of this expression would still just be 2x. I could have had big f of x equals sine of x minus 100 here. And if I were to take the derivative of this, I would still get cosine as my derivative. So what if there was a number that was added or subtracted here at the end of the function? How do we deal with that? Because we know that when we take the derivative of this, it would just go to 0. So there is a rule or a theorem that says that if we have a big f of x function and it's an antiderivative of a function, then we're going to have to account for the constant somehow. And how we do that is to write plus c at the end of our antiderivative. So when we take and we say a general antiderivative, because the general basically accounts for any sort of function that did have a constant at the end. Ooh, I can't spell antiderivative. We put a plus c at the end to account for any constant that could have been there that went to 0 in the derivative process. And there didn't always have to be a constant, so it could be a possible constant. So there could have been a number there, but there also could have been just like plus 0 here, because that would have also just gone to 0 when you do a derivative of that. So if we think about how we can apply this on just some other examples here. So if I have f of x equals 0 and I want to know what the big f of x was here that I started with, well, we know that the derivative of any constant would be 0. So this f of x could be 100. This f of x could be negative 1,000,000. This f of x could be 24. Its derivative is still going to be 0. So we actually say that this big f of x is just c. Because again, this is the constant or a constant that would go to 0 as a derivative. And I'll write that down here, since the derivative of any constant is 0. So if we look at the next example, now we're given secant squared. So if I think about my derivatives, if I kind of go back up here where I have my sine and cosine, the next one we talked about was cosine of x. We know that the sine of the derivative of that would be negative sine of x. And then we have tangent. And the derivative of tangent is secant squared. So if this is the function that we want to know what it was that we started with, if this is our derivative of something, well, our derivative of tangent would have been secant. So that means that the antiderivative of secant squared would be tangent. So our big, and here's a little bit of different notation here, our big G, and our also variables different here. So G of theta would have actually been tangent of theta. But again, I could have had a constant added at the end here. So I'm going to say tan of theta plus c. So this is, again, another one of the tricky ones, kind of like this x to the third that we did above. And again, like I said, I like to start thinking about the exponent because I know that in order to have gotten this derivative of 1/2, I would have been having to increase by 1. So if I think about 1/2 plus 1, which is really the same thing as 2/2, that would have meant that my original exponent would have been 3/2. Because if I take 3/2 and subtract 1, that's how I'd get an exponent of 1/2. But then I have to think about what number would have been over here to undo it to only get a 1 here. That would have had to have been 2/3. Because if I were to bring down 3/2 and multiply by 2/3, that's what would give me a 1 here. And again, I could have had some constant added at the end. So I'm going to put a plus c here. And then this is just a general kind of rule. What if I have any variable raised to any exponent? How do I get the antiderivative of that? And this is the antiderivative power rule that we're going to be using in the next couple of examples. So this antiderivative power rule says that we're going to do 1 over whatever the exponent of n is and add 1 to it. And we're going to multiply that by whatever the variable is raised to the exponent of n plus 1. And then plus c at the end. And this is what we call the antiderivative power rule. And that might be something that you'd want to have on your note card, is this antiderivative power rule, because that's what we're going to be using in each of the examples after this. Okay, so we're going to look at just finding some general antiderivatives. There is a table of antiderivatives in your textbook, so if you are interested in looking at that or writing some of those on your note card, it might be helpful. But just in general, when we're doing antiderivatives, we have to think about getting them into a form that we can work with by just using a power rule. So right now we don't know anything about quotients. Here's another quotient. We don't really know anything about roots, how to deal with those. So in general, before we even do any antiderivative work, we want to rewrite anything that's in fraction form. We want to rewrite anything that's in radical form, and we would want to rewrite anything with quantities raised to powers. So before using your antiderivative rules, we want to rewrite any quotients, roots, and quantities raised to powers. Meaning anything like something like x minus 1 to the third power, or x minus 1 to the second power. We'd want to actually like multiply that out. So if we want to find the antiderivative of this g of x function, the first thing that I'm noticing here is that I have a quotient here. So I want to rewrite this, and we have to be a little bit careful of our notation here, because when I'm just rewriting the g of x function, I'm going to use the same notation because I'm not doing any antiderivative work. I'm just taking this and I'm manipulating it, or I'm rewriting it. And the way that I want to rewrite something like this is to bring that power of 2 up to the numerator by using a negative exponent. So I'm going to rewrite this as 6x to the negative 2 power, and then minus sine of x. So then once I get it into a form that I can work with here, this is where I'm going to change my notation, because now I'm actually ready to do my antiderivative work. So here's just a rewrite of little g of x, but now I'm actually going to want to do my antiderivative rules. And anything that's got a constant in front of it kind of works the same as when we were doing derivative rules. I'm going to bring down the constant of 6, and I'm going to multiply it by the antiderivative of x to the negative 2. So this is what I want to apply my power rule on. So my exponent is negative 2, so I'm going to multiply this by 1 over negative 2 plus 1. And I'm going to multiply by x to the, so that should be negative 2 plus 1. So whatever's in your denominator is actually going to be the same as the exponent there. And then I'm going to subtract, and then I want to know what the antiderivative of sine is. So if I go back to my trig derivatives here, well, we see that we have a negative sign here. So if we want to take the antiderivative of just positive sign, that's going to change the sign of the SIGN of this one. So if my derivative here is sine, my antiderivative would be negative cosine. If my derivative is negative sine, my antiderivative is going to be positive cosine. So the signs are just going to change here. So that means that the antiderivative of sine of x would actually be negative cosine of x. And this double negative, you just have to be careful about in here, because we're obviously going to want to turn that into a plus in the next step. So then I want to definitely clean this up. So anything that I can combine into like a cleaner fraction, I want to do that. So I'm going to bring over the 6 times 1 over negative 2 plus 1 is negative 1. X to the negative 2 plus 1 is negative 1. It's going to become plus cosine x, and then plus c. And then I just want to clean this up a little bit. So big G of x would be, this is really 6 times negative 1, so negative 6, x to the negative first power plus cosine of x plus c. And I would definitely accept this as an answer, but just know that you can manipulate negative exponents back into positive exponents if you need to for some reason. So you could also write this as negative 6 over x plus cosine of x plus c. And that really means the same thing. You're just manipulating the x to be back down into the denominator with a positive exponent on it. And the nice thing about this is you can always check to see if your work with your antiderivative rule does seem reasonable. So if this is my big G of x, and I want to take the derivative of that to double check to see if like what I started with was what I really get when I take the derivative of this. If I bring down the negative 1 exponent multiplied by 6, that gives me 6x, decrease the exponent by 1, so negative 2. Derivative of cosine is negative sine. And then the derivative of any constant would just be 0. So this should match what you started with up here. So that checks out. All right, the next example, we're going to have to do a little bit of work over here because, again, we do have a fraction. So I'm going to, again, this is just a rewrite of little h of x. So I'll pull down the 2 sine of x. I'm also noticing that in addition to there being a fraction here, I do have a root. So I'm going to actually rewrite this first as x to the 1/3 power. So I'll keep this as 3x to the 4th plus x to the 1/3. And then all divided by x. And then I do want to get rid of this fraction. So I think the best bet, and we kind of talked a little bit about this when we were doing derivative rules, is to split this up into 2 fractions, each with their own denominator of x. So I'm going to make this 3x to the 4th over x, and then plus x to the 1/3 over x. And then what I want to do is I want to simplify here, kind of like what we were doing when we were doing limits to infinity. So I'm going to make this 2 sine of x plus 3x to the 4th over x becomes 3x to the 3rd. And then here I would want to use a property of exponents here that says I'm really taking x to the 1/3 and I'm subtracting out the exponent that's in the denominator, which really is a 1. So x to the 1/3 minus 3/3 is going to give me an exponent of negative 2/3. So this becomes x to the negative 2/3 because that quotient property says that I can subtract those exponents. So again, I haven't even done any antiderivative work yet. This is literally just a rewrite of little h of x. So now, once I've gotten it into the form that I just have powers and I don't have any roots and I don't have any fractions or quotients, now I want to do my antiderivative work on this. So I'm going to call this big h of x, and I'm going to just work my way term by term here. So I'm going to bring over the 2. I want to take the antiderivative of sine, which in the last problem we said was negative cosine. And then I'm going to bring over my plus, bring over that 3, and I want to do my antiderivative power rule on the x to the 3rd. So this is going to be 1 over 3 plus 1 times x to the 3 plus 1. Bring over my plus, and then I want to apply my antiderivative power rule on this negative 2/3. So 1 over negative 2/3 plus 1, x to the negative 2/3 plus 1, and then plus c. And then I'm just going to start cleaning this up. So I'll rewrite that first term as negative 2 cosine of x. First thing I'm going to clean up is this part of the fraction here. So that's going to become 3 times 1/4, x to the 4th. And then I'm going to work in the denominator over here. So negative 2/3 plus 1 is really negative 2/3 plus 3/3, which is going to become a 1/3. So it's going to become 1 over 1/3. And then x to the 1/3 plus c. And then there's 2 other things I need to do here. I want to multiply this out, and I never want to leave a complex fraction. Meaning I never want to leave anything as a number over a fraction. So I'm going to definitely simplify that. So this is going to become negative 2 cosine of x. It's going to become 3/4 x to the 4th. And then here, this is really a keep, change, flip thing happening. This is really 1 divided by 1/3. And if I keep, change, flip that, that's going to become 1 times 3 over 1. So that's actually just going to become a plus 3, x to the 1/3, and then plus c. And there's my antiderivative. And again, you can check that using a differentiation or using derivatives to make sure that you get this when you do take the derivative of that. So I'll do one more general antiderivative example. The only thing here that I want to talk about first is this square root of x. So I don't want to leave that like that. I'm going to rewrite that as a fractional exponent. So again, this is still just little m of x. So that's going to be 4x to the 1/2 minus secant x tan x. And now I want to do my antiderivative work, so I'm going to call that big M of x. So again, I'm going to bring over the 4 times, and then I want to do my power rule on this x to the 1/2. So 1 over 1/2 plus 1, x to the 1/2 plus 1. And then I want to subtract from that the antiderivative of secant tan. So if you think about, again, our trig derivative rules, if we had a function that was secant of x, derivative of secant is actually secant of x tan x. So that means that if we're looking for the antiderivative of secant tan, the antiderivative of that is actually secant. So it's going to be minus secant of x and then plus c. And again, I just have a little bit of work to do over here. So first thing I want to do is clean up that denominator. It's going to become 4 times 1 over 1/2 plus 1 is really 1/2 plus 2/2. So that's going to become 3/2. X to the 3/2 minus secant of x plus c. And again, I never want to leave anything like this. So again, that's really 1 divided by 3 over 2, or keep, change, flip is 1 times 2 over 3. So that means we're going to take the 4, multiply it by the 2 over 3 times x to the 3/2 minus secant of x plus c. And that tells me that my antiderivative would be 8/3 x to the 3/2 minus secant of x plus c. And again, you can check that using your derivatives. And that should give you what you got, or what you started with your little m of x. All right, just one more example. And this is something called a differential equation. And that's an equation that involves the derivative of a function. So we've been talking about adding on this plus c at the end of our general antiderivatives. But when we're solving differential equations, basically what the goal is given some sort of derivative and some sort of, sometimes they call it boundary, or sometimes it's called an initial condition, we want to actually figure out what the original f of x function was, and we also want to know what c is. So my goal for these is to find the original f of x function from a derivative. And that might be a first derivative, it might be a second derivative, and then we're going to be using some sort of boundary conditions to find c. Okay, so let's start with this derivative. So this is our first derivative, and basically what we're looking for is we're looking to go backwards to figure out what our original f of x function was. So we're going to start with this f prime, and that's x squared plus 2x plus 1. And I want to use antiderivative rules to actually find out what going backwards, what the original f of x function was. So I'm working backwards from an f prime, and I want to use my antiderivative rules to find the antiderivatives of this to find out what my original function was. So that means that if I do my antiderivative rule, this is going to become 1 over 2 plus 1, x to the 2 plus 1, plus, bring over the 2, multiply that by, technically the exponent here is 1. So this is going to become 1 over 1 plus 1, x to the 1 plus 1. And then my antiderivative of 1 would actually just be 1x. And then I need to put on my plus c there. So if I clean this up a little bit, this is going to become 1 over 3 x to the third plus 2 over 1 over 2 x to the second power plus x plus c. And this actually just becomes 1/3 x to the third plus just x squared plus x plus c. So here's my starting antiderivative. This is my original function f. And if I were to take the derivative of that, I would get x squared plus 2x plus 1. But what I want to know now is, well, what is this c value? So I want to find c. And in order to do that, I want to use my initial condition saying that f of 3 is equal to -1, which really tells me that in my original f of x function, when the x value is 3, the y value is -1. So what I can do with this information is, now that I know what my original f of x function was, I want to use f of 3 is equal to -1 to find c. And that basically means that I want to plug in an x value of 3 for any x's that I have in my function, and I want to plug in -1 for my y, or for my f of x. So I'm going to replace this f of x with -1, since that's my y value, and I'm going to go ahead and I'm going to replace every x here with 3. So 1/3 times 3 to the third plus 3 squared plus 3. And then I want to find c, so I'm going to leave that as my variable. And then I'm just going to do a little bit of algebra over here. So this is going to become -1 equals 1/3 times 27. 3 to the third is 27. Be careful about that. Plus 3 squared is 9. Plus 3 plus c. 1/3 of 27 is 9. So 9 plus 9 is 18. Plus 3 is 21. So if I subtract 21 from each side, that tells me that c is -22. And putting this information with this f of x function, this tells me that my solution that I'm looking for here is my f of x is going to be equal to 1/3 x to the third plus x squared plus x. And then instead of writing plus c here, I'm actually going to plug in my -22. And that's my goal with solving a differential equation, is to figure out what that c value is to get a particular solution here. All right, so your homework is in the book. It is listed on Google Classroom, so you can start working on that if you have some time. Let me know if you have any questions.